Hi everyone. Last week we were talking about parameterizing curves and component functions, and I expressed doubt that we can just blithely name component functions to parameterize any curve no matter what it is. I've looked into this some more, and completely unexpectedly, I've stumbled onto a much better understanding of the reason that we're here, Fermat's last theorem. So today, I'm going to talk about parameterizations of curves and Fermat's last theorem, and I think by the end, we'll have a much better understanding of what Fermat's last theorem is about. We're not going to understand it by any means, and we certainly won't be able to follow it, but we're going to understand a little better where it's coming from. So to remind us where we've been so far, what we're trying to do right now is just get up to speed on all the elements of Wiles' proof. Elliptic curves, modular forms, and how they relate to Pythagoras and Fermat. The first few points about elliptic curves weren't hard to grasp. The group structure of elliptic curves, and remember this was the first few videos we did where if you can basically add 2 points on an elliptic curve and get a third one. Then we started looking at the relationship between complex numbers and elliptic curves and discovered that even though Fermat is all about algebra and rational numbers, a squared plus b squared equals c squared, the proof is actually all about complex numbers. And the way in which elliptic curves are related to complex numbers is way more complicated than anything we've done so far. And then in addition to complex numbers and elliptic curves, modular forms are also explicitly about complex numbers. They're numbers that have to do with the upper half plane in the complex number. That's modular forms. And the proof is, what Wiles proved that demonstrated that Fermat's last theorem was true, is that every modular form is an elliptic curve. So what in the world does that mean? That's what we're trying to understand. So because this has so much to do with complex numbers, I thought we should shore up our understanding of complex numbers because we're not going to get anywhere without a good understanding of complex numbers. And in order to understand complex numbers, we really need to understand multivariable calculus. That's where we are now. And we just barely started looking at multivariable calculus, and I ran into this question, which has bothered me for a long time. So the answer to the question, can any curve be parameterized, is well, yes, maybe. Any continuous closed curve can be parameterized using Fourier series. Mathologer has a great video about this. So I think that puts the answer to bed, actually, because then if we can parameterize any closed curve with some restrictions using Fourier series, then all we have to do is, cut it off here and here, and we would have a parameterization for this curve, right? And then you just sort of connect it, and then you've got your parameterization. The thing is, that's not really the question. That's not really the important question. Or there are more interesting questions than this one. Because when we ask, can we parameterize any curve, we don't mean if I have infinite time and an infinite amount of paper, can I write down sine and cosines in order to get this curve? That's not what we mean. The question is, can we parameterize any curve using normal functions, sine, cosine, polynomials, and so on? And the answer to that is no. And looking into why the answer is no is what really gives us a hint about what the proof of Fermat's last theorem is about. So one of the basic old questions about mathematics is, what can we do with polynomials? And it's looking at polynomials that led us directly to real numbers and even complex numbers, because the simplest polynomial messes us up. Neither one of these have solutions in rational numbers, right? That's what led us to create real numbers and complex numbers so that we could solve polynomials. Now, regarding parameterization, we know how to parameterize a circle easily. It's just that xy equals cosine t sine t. So that's good, but these are transcendental functions. Can we parameterize a circle with polynomials? We can certainly parameterize a parabola, because the parameterization of a parabola is just t comma t squared. And then you can see it's pretty easy to see that as x goes out, then y goes up, just in a parabola. So we can do a parabola. Can we parameterize a circle using polynomials? It's actually pretty easy to see that the answer to that is no. Because if we had just a generic, both of these polynomials are going to go up either to positive infinity or negative infinity, right? That's what polynomials look like. They might wiggle in the middle and then they go off. The problem is a circle has a definitely finite range. So it's simply impossible to parameterize this with a polynomial because the polynomials are going to go out to infinity. The circle definitely does not go out to infinity. So we're already stuck. So what do we do about this? And this leads to the first connection with Wiles' proof, because one of the words that he uses frequently that I didn't understand what it meant is affine. And I understand now better what affine means in the point. Affine is basically the opposite of projective. And all affine means is that there are parallel lines. Whereas in projective space, remember, all we're saying is that if you have two parallel lines, in affine space, they never meet. But in projective space, you add a point at infinity out here somewhere so that they eventually meet out here at this point called infinity. Okay, that's what affine is. So we can overcome the shortcomings of polynomials by using homogeneous coordinates, which is projective space. If we want to do a circle, instead of representing it by two component functions, we can use projective space and make it 3. So now x, y, and w are polynomials, and then t is on some interval, a to b, and so on. So now we can convert projective homogeneous coordinates back into sort of standard components by just dividing through by the third term. So this is equivalent to ct equals xt over wt, and then yt, wt. And then, of course, if wt is constant, then this would just be a basic parameterization. So what do we have here? These are quotients of polynomials. This is a polynomial, and this is a polynomial. These are called rational functions. And curves that can be expressed with rational functions are called rational curves. So it turns out we can, in fact, parameterize a circle using fractions of two polynomials. Okay, if we have a circle of radius 1, if we draw a line from the point at 0, 1 up to somewhere on the x-axis, call that t0. And then since a line intersects a circle at 2 points, so we'll just call that point xt, yt. So this is the amazing thing. Any point on the x-axis is going to correspond to a point on the circle. The only point that's not going to be intersected is the South Pole. There's just one point at the South Pole. And that point corresponds to x at infinity. If we go out here all the way out to infinity, then the slope of that line is going to go down and be horizontal and meet in projective space out here at infinity, right? That's amazing, isn't it? Everything except the point at infinity will be covered by some point on the x-axis. And then by adding projective coordinates, we get the point at infinity, and that fills in the point at 0, -1. Okay, so can we turn this into an actual parameterization? Can we find x and y here? Let's go to another page. So first, what is the equation of this line? We already know the slope, because the slope from here to here is always going to be 1 over the run, which is t. So the slope is 1 over t. And we already know that the y-intercept is -1. So the equation then is y equals 1 over t, x minus 1. So now if we just rearrange these, we get x equals ty plus t. Okay, now the equation of the circle is x squared plus y squared equals 1. So let's just plug this into here and see what we get. So we have ty plus t squared plus y squared equals 1. Now we just need to solve for y. So I'm just going to do this fast. If you have any questions, then you can ask me. Okay, so the two roots of y are either -1, because this one turned out to be minus 1 plus t squared over 1 plus t squared, or 1 minus t squared over 1 plus t squared. Those are the two roots. So plug the other one back into the equation for x, and we get and that's it. So the rational parameterization of a circle is x equals 2t over 1 plus t squared, and y equals 1 minus t squared, 1 plus t squared. And then we can check when t moves off to infinity, this will be 0 and this will be -1. And to do that, you use L'Hopital's rule, which is another one of those first year calc things that I'm assuming we already know. If you have any comments about it, tell me in the comments and we can go over it. But basically, L'Hopital's rule says that if f over g is infinity over infinity, then f over g equals the derivative of f over the derivative of g, which at infinity is 0 minus 1. So this is just amazing to me. I thought there was this inextricable link between a circle and cosine and sine. And it turns out not necessarily. You can do the whole thing with rational functions, with quotients of polynomials. When I got my very first computer, it was an Atari 800, and I used to try to draw circles with BASIC. And I learned somewhere that the way to do that is you can do it with a for loop basically by parameterizing the circle. So you do 4x equals like 1 to 360, and then you do cosine x sine x, and it'll make the circle. And I was so young, I had no idea what any of this meant or why it worked, but I've always, my whole life, known that cosine and sine parameterizes a circle. It just blows me away that I could have made a circle using these equations with math that I understood, even though I wouldn't have understood how we got the circle out of it at the same time. And the thing is, all we use to do this is polynomials, implicit polynomials. X squared plus y squared, and then the function of the line. So we did just use polynomials, so of course we can do it this way. And the amazing thing is that this polynomial connects us to sine and cosine. And so there's a lot more going on here than just another way to draw a circle with a computer, because these are transcendental. That makes sense. It's a circle, we're using pi, it's periodic over pi, and so on. That all makes sense. But here we're doing it just with polynomials, which never mention pi. I think that's quite amazing. And that's just the beginning, because furthermore, since we know that this is a parameterization of a circle and this is a parameterization of a circle, now we know that we can use these to parameterize sine and cosine. So we can say that cosine x is 2t over 1 plus t squared. Sine x is 1 minus t squared over 1 plus t squared. So now we have rational parameterizations even for sine and cosine. That means anything that we can do with sine and cosine, we can do with rational parameterizations. So with the parameterizations of sine and cosine in hand, we can easily do parameterizations of the other conic sections. So let's just do a hyperbola. So the standard form of a hyperbola is x squared over a squared minus y squared over b squared equals 1. And then a parameterization of a hyperbola using trig functions is x equals a secant t and y equals b tangent t. So the rest is easy because tangent equals sine over cosine and secant equals 1 over cosine. So then x just equals the a times the reciprocal of that, and y equals b times sine over cosine. So again, the reciprocal of x. Those cancel, and we get b 1 minus t squared over 2t. So this is a rational parameterization of a hyperbola. Really amazing. Okay, well that takes care of polynomials of degree 2. Let's look at a polynomial of degree 3. What's this? This is an elliptic curve, right? And if we just factor it, it's x, 2x plus 1, and 2x minus 1. Okay, so all we did, here we have x squared and y squared. So here we just raised the x to the third. And so this graph looks like this. And if we add a point at infinity, these both go off to infinity, right? So if we add a point at infinity, they go up, and then they basically just somehow bend around and end up back here in infinity. Basically, topologically, meaning the shape of the curves, is just two circles. Okay. Now, I'm going to back up a little bit. One of the most important properties of sine and cosine and so on is that f of z plus 2 pi equals f of z. They're periodic. So here's another new connection to Fermat's last theorem. In the complex plane, there are functions that are doubly periodic. That means they're periodic in two directions, meaning that every time you go up in this lattice, you're going to get the same value, and every time you go over, you're going to get the same value, and if you go diagonal, it repeats in both directions. Now, we talked about this once before too, and this is where we're leading. This is one of the reasons that we're looking at complex numbers at all, is so we can understand these functions with periods 2 omega 1 and 2 omega 2. So it's just like pi, right, in one dimension. It's the same thing in two dimensions. And a doubly periodic function that only has a pole at the lattice points is called an elliptic function. This gets very misleading because we have elliptic functions, we have elliptic curves, and we have elliptic integrals. The reason they're called elliptic is because all of this stems from trying to find the arc length on a ellipse. Once we started looking more at complex analysis, they realized more connections here, and so elliptic functions have to do with this. They still sort of stem from this same original problem, but in a completely different way. These do not mean the same thing. But the periods of 2 omega 1 and 2 omega 2 play much the same role in the study of elliptic functions that 2 pi does in the study of sine and cosine. So now parallelograms are isomorphic in some way to tori. And the reason is, if you stitch them together, if you stitch this side to this side, you're going to get a tube, right? And then if you stitch this side to this side, bend it around, you're going to end up with a torus. So topologically, these doubly periodic functions are isomorphic to a torus. You can embed these in the torus. And basically the way that works is, if you go one direction, you could be going around here periodically. And then if you went the other direction, you could go around it in the other direction, okay? Now, the simplest of these doubly periodic functions are the Weierstrass elliptic functions, which look crazy. That looks like a complete mess. But based on what we just said about how f of z plus omega equals f of z, you can start to see that it's starting to make a little bit of sense. It's not really maybe so complicated, because this is in some way moving it back. For every iteration of omega, this moves it back to the original z. And we're not going to look any more at this right now because it is ugly, but basically that's what it is. For the whole lattice, it's just taking each point and putting it on so that it's defining it within this one parallelogram, okay? The amazing thing is, when you take the derivative of this function, you end up with something completely insane, which is, whoops, wrong one. This is the Weierstrass function. This is the derivative of the Weierstrass function. And what we have here is an elliptic curve. This squared equals this cubed minus the same thing with some coefficients. That's just amazing. And so, just as we used sine and cosine to parameterize a circle, we can use the Weierstrass function and its derivative to parameterize an elliptic curve with x equals t and y equals the derivative of p. This is exactly the relationship with the circle, because we have y equals sine and x equals cosine, and x is the derivative of y. So you could just as easily just name sine the generic periodic function of one variable, and then say that we are going to parameterize a circle by saying, like, let's just call it, I don't know, g. And we could parameterize it this way. G of t and x is g prime of t. It's the same thing. So when we go up to complex numbers and now we're periodic in both directions, we're actually doing the same thing. So these Weierstrass functions, which look very strange, are in some way something similar to sine and cosine for circles and conic sections. And these elliptic curves can be parameterized using these elliptic functions. So remember that in the curve, if we add a point at infinity, then this one comes around like this to a point at infinity. So if we extend this to complex numbers and we end up with a torus, it basically looks like the two circles here basically go around the donut this way on each end, right? So one of them would be this one and one of them would be that one. So basically, I think that if we could picture complex functions, this would basically look like a tube coming out of the paper and going back into the paper. But remember that we can't actually picture it. It's more complicated than that because a complex function is four-dimensional. And so basically, each elliptic curve is associated with a particular elliptic function, or each elliptic function produces one elliptic curve. So all you have to do is find the two periods and you've got your elliptic curve. And each elliptic curve has the elliptic function with two particular poles, with two particular periods. That's all you need to do is you find your two periods. You don't have to know anything else about this. You find your two periods and you've got your elliptic curve. Which again, if you think about sine and cosine, that's how sine and cosine work too, right? They're very simple because the wave is already built into the sine and the cosine. All we're doing is adding the parameters about the frequency and the magnitude. Same thing going on here. So just to tell you, for the elliptic curve that we started by looking at, y squared equals 4x cubed minus x, the two periods for the elliptic function that will make this elliptic curve are so it's insanely complicated. This is an elliptic integral. There's this part, right? But this is the parameterization for this elliptic curve. So elliptic curves can be parameterized using elliptic functions. But back to the original question, can they be parameterized using rational functions? The answer to that is no, and I'm going to show you why. Okay, so to show you why, there's two things that I need to introduce. One is called the Riemann sphere. It's a sphere. Up here is infinity, down here is 0, over here is 1, here is -1, here is -I, and back here is positive I. What this is just the complex plane with infinity added to it. This is the projective complex plane. So all we did is we took the complex plane and then basically bent it around so there's one point at infinity. So this is the unit circle right in the middle. This is 0 down at the South Pole, and up at the top is infinity. That's all a Riemann sphere is. We're just adding infinity and curling up the complex plane so that it all meets at a point. One more thing is the Jordan curve theorem. This is something super easy to understand. All it says is, if you have a simple closed curve, that curve has an inside and an outside, okay? That basically it's saying that a curve, a closed curve, cuts the plane into two regions. The region inside the plane, inside the curve, and the region outside the curve. So just keep those two things in mind. So the question is, can we parameterize an elliptic curve using rational functions? Now we know that the elliptic curve in complex numbers makes a torus. So let's suppose we could parameterize this curve with rational functions. If we could, then we could take our curve and lift it up onto the Riemann sphere. And then on the sphere at some point, there would be mapped the circle here. Like one of these circles would be here somewhere. That means the Jordan curve theorem says that on a sphere, any curve on the sphere cuts the sphere in half into an interior and an exterior. So if we took one of these circles and mapped it onto the Riemann sphere, there would have to be an interior to the circle and an exterior to the circle. But look at the torus. If you cut the torus around here, there's no interior and there's no exterior because you can stay on the inside of this curve. You can go all the way around and end up at the other side. There are no points on this torus that are outside of this curve. So the Jordan curve theorem works for a simple plane, and for a sphere, it does not work for a torus. But the elliptic curve is a torus. So it's simply not possible. As a result, rational parameterizations of elliptic curves are simply not possible. Isn't that amazing? We went through like 3 steps and it's so easy to understand this, but it makes the rational parameterization of this curve impossible. What about Fermat's last theorem? We can't parameterize an elliptic curve with rational functions because topologically they're the wrong shape. And that is what Wiles and Ribet's proof is about. So, of course, we don't remotely understand the details, but I think we're beginning to understand what the proof is doing. No detail here, but in some vague way, elliptic curves can be parameterized by elliptic functions. What Taniyama Shimura conjectured is that elliptic curves can also be parameterized by modular functions. And this is what Wiles proved. He proved that all elliptic curves are modular. So let me tell you here what a modular function is with absolutely no motivation, but I'm just going to write it down so you've seen it. So modular functions are on the upper half plane. So a modular function f is meromorphic, which means that it can have some poles, some places where it goes up to 0, up to infinity, but a finite number of them. And then if you take a matrix in what is called the modular group, which means that these are integers and the determinant is 1, which means that AD minus BC equals 1, okay? Then the modular function f has the property that AZ plus B over CZ plus D equals f of z. Okay, no idea how any of this works together, what the point of this is, or what it means in any way. But there's one observation that we can make today after what we've been talking about, which is that this looks like some sort of a periodization, right? And that is in fact what it is. That in some way, when we do this operation to z, we'll end up back at z. That's just like we were talking about with periods. You add omega to z, you get back to z. So here, you do this to z, and you get back to z. And that is what modular functions are. They are also periodic in a very different way from elliptic functions. What Wiles proved is that every elliptic curve can be parameterized by a modular function. And then what Ribet proved is that if you have a triple that is a non-trivial solution to Fermat's equation P is an odd prime, then the Frey curve, you can translate that into this kind of a curve, an elliptic curve with AP here and BP here. This is clearly an elliptic curve, right? It's just like the one we were just looking at, where it's x minus one thing, x minus another thing. And then what Ribet proved is that this elliptic curve cannot be parameterized by a modular function. But what Wiles proved is that every elliptic curve can be parameterized by a modular function. But if there's a solution to Fermat, then this equation would make an elliptic curve that is not modular.
So we have reached a contradiction.
And therefore, Fermat's last theorem is proven. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.